Okay, so thank you for coming to this presentation today. I'm always fascinated by what your interest might be in this presentation, and maybe after we can catch up in the hallway, and love to talk to anybody that has some constructive feedback or questions. So I'm Jeff Greer. I am a professor at the University of North Carolina in Wilmington. I teach maritime cybersecurity. So today I'm going to talk a little bit about creating a virtual ship environment that's optimized for cybersecurity use. So here's my problem statement. Undergraduate students do not have a maritime domain knowledge. They're just, unless somebody's coming out of the Navy, the Coast Guard or something, they just don't have it. And it's impossible for them to either attack or defend a ship if they can't visualize it and describe it in terms of its digital operating environment. Ship access for students outside of maritime academies is limited due to port security and/or insurance reasons. So how do you develop a world-class environment for teaching maritime cybersecurity? So I initiated a joint study with a company out of Poland, Unitest marine simulators. I decided to work on a virtual environment first and then physical test beds. So UNCW, we're located in Wilmington. We have a Center for Cyber Defense Education, a McCartich Research Hub, and specialized maritime cybersecurity classes. And so I'm leading up the study. These are the phase 1 results, and then I'm spinning up a research team for phase 2. And then Unitest, a supplier of marine technology located in Gdynia, Poland. The founders came out of Gdynia Maritime Academy, and they offer state-of-the-art marine engine simulators for merchant seamen education and assessment. So the leadership team over there is supporting my study and gave me permission to talk about this today. So here's my system of interest for the study, Unitest Marine Simulator. And so the thing that most people may or may not know is that the simulator design is shaped by training need and regulatory compliance. So the Unitest simulator that I'm working with, it says the engine room simulator has been developed to comply with STCW code. So for those that aren't familiar with STCW, it's the standard training for certification for watchkeeping. Every merchant seaman needs to pass that exam to get permission to go to sea. And then they have within the STCW code certain sections. And so it's the code that's really shaping the maritime cybersecurity education that's taking place within the maritime academies. So what I looked at is an alternate use case study where what if we took that simulator and we utilized it for teaching maritime cybersecurity? So I came up with 3 use cases. The first use case is what if we use the simulator for just teaching ship domain knowledge to cybersecurity students who are non-mariners. And so that's got some potential. The second use case is I wanted to look at simulator use for teaching security by design using model-based system engineering or system-of-system engineering concepts. And then use case 3, simulator used for teaching and assessing student response to relevant cyber attack scenarios. So in my study methodology, I had use case 1, 2, and 3 down the left-hand column. Then I looked across and I said, let's take a look at the use case simulator functional requirements. This is just high level. What are their current capabilities, and then what are the gaps that we're taking a look at? So one of the things that really shaped my thinking on this, for those that aren't familiar with system thinking, system engineering, whether it's document-based or model-based, there's another aspect to it, and that's system of systems. So if you think of a ship as an apex system that has 20, 30, 40 subsystems within it, that's all knowledge you need to know from a cybersecurity point of view. So there's 3 guys out of Purdue University that wrote this book, and I highly recommend it for anybody that's interested in systems thinking and cybersecurity. And then a company called Spec Innovations out of Manassas, Virginia. They're a study sponsor. They've provided me with model-based system engineering tools for use in the study. So here's cybersecurity education simplified. One of the things you have to be able to do as an educator is taking something that's very complex and simplify it for ease of understanding and action. So Dr. Jeff Kroom from IBM came up with 3 of these, and then I added 2 more to the list. But the 5 critical thinking skills that I try and teach all of my students to be able to ask and answer. So the first one is, what is it? What is a ship? Why is it important? Why are some of the subsystems more important than others? If you're setting up your security scopes, how does it work? How can it fail, and how can failure be prevented? So, what you don't want is some cyber hazard contributing to a loss. And so then what you find is that there's varying role-based educational needs. Students, they need help with all 5. They don't understand the maritime domain. If it's an industry employee, they're a little further up the curve and they're just more interested in the cybersecurity component. And so what you find is that traditionally at the maritime academies, they focused on incident response on board the vessel. But today we have to look at it much more broadly when you think of naval architects, designing safe and secure cyber ships, whether it's autonomous ship or a drone, surface, subsurface, how does that get done? And then ultimately, you've got the shipbuilders now as we try and revitalize shipbuilding in the US, as well as surveyors. What's surveyors' role going to be in cybersecurity? And then you have masters and mates on board the vessel. You've got the landside fleet management company. So there's a spectrum of educational needs that need to be addressed. So I take a transdisciplinary approach to cybersecurity education, starting with maritime domain knowledge. Then I assume most of my students, because it's a senior level class, have some level of applied cyber risk management theory. What I then need to do is teach them how to take that theory and apply it into the maritime domain. So if you look at the questions I ask, questions 1 and 2 address the maritime domain, questions 3 and 4 address system engineering, and then question 5, like how do you prevent failure? That's where your cyber risk management comes into play. So there's my alignment. So let's take a look at the Unitest X92 simulator. And I'm going to go through this pretty quick. This is, if the system of interest is a stereotypical ship, this is a container ship of various characteristics. And then if it's the Apex Cyber physical system, the Apex system of systems, then it has within this simulator 20 subsystems. So you've got the bridge, the diesel generator, emergency, main engine. I'm not going to read them all, but there's a bunch of systems sitting in there. In the simulator, it tells you where these subsystems are located, in the decking plans. It's maybe a little tough to see here, but they've got very detailed decking plans. This is a view of the bridge and how it links down to the engine control room through the telegraph, right? That's the old maritime term for how the bridge talks down to the engine room. So, you've got the helm, and then you've got the steering gear, and you can turn them and make them move in real time. Here's the actual engine control room. On the right is the engine control. On the left is all the switch gear for the electrical panel. Here's the main engine control diagram. And there's a reason I'm showing the control diagrams, which I'll come back to in a minute. Here's the main engine top view. It's a 3-dimensional model. Here's the side view. And this is a Winterthur gas and diesel, 10-cylinder, 2-cycle engine, low RPM, fixed pitch propeller, commonly used in maritime. And in fact, Winterthur was owned by Wärtsilä. It was sold here recently, and it's now owned by China Shipping. So as the Chinese, become even more prolific in shipbuilding, they now have their own engine company. And this simulator is the training simulator for anybody who buys one of these engines. This is just a subsystem example. This is a generator. There's 2 gen sets, primary backup. Typically the 5th generator is your emergency, feeding the bridge and various other critical things. Operational status dashboard, as you fire it up. And then they have training scenarios and assessments. This is what IMO, or the STCW code regulates. And I picked the one screen that has fault simulation. And as you look at the fault simulation, there's not a one there that's cyber related, right? So there's a little bit of an opportunity to think about how you can induce faults into the simulator for educational purposes, cyber faults. So here's my preliminary study results, functional gaps and opportunities. So when I took a look at this X92 simulator, just very simply, 3 observations of note. The first one is it's not a full ship simulator. So if you're going to teach ship cybersecurity in the ideal world, you'd want to be able to have a full ship simulator, both a complete bridge, above the waterline, below the waterline system, including communications. So today, to make up for a full ship, I have to use multiple simulators. So like I have the analog to this, which is a bridge simulator that I've been looking at as well. Let's see here. The second thing is the control diagrams are useful, but not practical for cybersecurity purposes. What we really need to see is the network diagram, and we need to see the freestanding digital logic controllers that are probably down in the engine room. So the question is, what's it going to take to get that? And then the simulator fault library does not include any cyber-related items. So how this maps out, if we could get that full ship simulator, it would help use case 1, 2, and 3. Control diagrams, we can use the simulator for maritime domain knowledge, but we really need to step it up if we're going to do security by design and develop a cyber risk management strategy. And then that incident response, that definitely needs to be built up. So those are the impacted sections. So for phase 2, what am I going to look at? I came across a really good document from NIST. It's called the Cyber Range, and it references the notion of cyber range types, right? So you have simulation ranges, overlay ranges, emulation ranges, hybrid, spanning, like a synthetic world to physical reality. So as I start to take a look at, the phase 1 results and what additional functionality do we start to add in, this is useful because now all of a sudden I have to learn about all the different types of simulators and where are the opportunities for developing this further. So I could take the Unitest X92 simulator and maybe link it with a Unitest, that's another Dutch company, bridge simulator, or Fortzilla or somebody else's. So it's just the interfacing requirements to make that happen. Alternatively, I can integrate Unitest X92 simulator, which is a synthetic ship environment, with the physical world, which might include test beds, network simulators, industrial controllers, physical security control systems, etc. So, gentleman's here, he worked with Boeing. They did that with the V-22, taking a crashed V-22 Osprey and taking the synthetic world and bridging it back so you could actually see what was going on. So that's what phase 2 is going to look like. It's going to take a little bit of time to complete. I'll be teaching and researching, and I figure I'll get it done in the spring of 2026. The people in Poland are really excited to, get the results of this next stage. So if anybody wants to see it, I'm here in the Maritime Hacking Village. Alternatively, you can email me at greerj@uncw.edu. I did put acronyms, a little appendix in here, but more importantly, Appendix B, I can't stress enough the use of model-based system of systems engineering for cybersecurity purposes to address large-scale complex systems. So one of the benefits of systems engineering is the power of abstraction, where you take a really complex digital environment and reduce it to something that's easier to understand for the problem you're trying to resolve. So I've developed 6 methods. Actually, there's a few more, but I just mentioned them to you if this is something new to you for the first time. But I have security domain boundary and attack surface analysis, modeling techniques, organization function, time-based, how their behavior impacts the attack surface structure and condition, system operational dependency analysis, what they call SOTA. If you look at NIST CSF 2.0, the identify function, they talk about having a list of your digital assets. What they don't talk about at the level they should is it's the interdependency or the coupling of those assets with each other, right? And so you need to really get in there and sort that out. And it's important because, you can have an apex, you can have a major system, then you have feeder systems coming in. If you're going to attack, do you attack down in the feeder system or at the main level? And then also, if you're looking at safety or resiliency engineering, you have to understand how things are going to fail. So you have single point failures, common cause failures, cascading failures, and you need to engineer this for a safe operating environment. So that's an interesting one. The other one is criticality analysis for systems and components. You have to go through all the systems and components, and you can't treat all cyber risk, but where you do want to treat, what's critical, right? What's mission critical? And so as a result, you have to focus there to establish your security scopes and how you're going to manage the various risks. Then the final, or the other one, next one up is cyber hazard loss analysis. If you know anything about system of systems, there's been work done on how do you do verification and validation testing on system of systems, not as discrete components. So there's a woman up at MIT, Nancy Levinson, and she's a world expert in safety engineering. And she came up with a method, STPASEC, system theoretic process analysis, and then it was adapted to cybersecurity by Dr. William Young, who founded the Air Force Cyber Institute. And as a result, it's a way to really go through that complex system of systems and sort out cybersecurity, safety, and resiliency engineering methods. And then finally, there's cyber hazard loss analysis. Your cyber risk management strategy design should be informed by cyber hazards. And then if you look at the sources of that information, loss information, you can, OSINT-wise, you can get it from the insurance companies. Here's things you don't want to have happen. And if you have cyber hazards, where's your threat intel sources and what does that tell you? And then finally, once you have all that information, you can sit down and design out your cyber risk management strategy design. So that's it. Anybody has any questions, you're welcome. I did put some examples in here. Here's my security domain boundary attack surface model, which is what we call the I-box method. You put an imaginary box around the vessel or the system of interest on the vessel, like the engine room. Anything that can break the plane of the box physically is a potential cyber attack vector. And then you can there's like 4 types of attack vectors, whether it's the digital cable breaking through the plane, RF energy breaking the plane. You can look at the cyber supply chain, Trojan horse attack, what gets delivered to the vessel. You have authorized people to be on the vessel that can fall prey to social engineering attacks. And then you have unauthorized people trying to break through the security domain boundary. So then if you look at organization function analysis, I'm looking at how organization behavior over time impacts the attack surface structure and condition. I'm going to run out of time here in a minute, but we've got that technique. Talk a little bit about SOTA, system operational dependency. What are the coupling mechanisms? It can be, the network is a coupling mechanism, but logically it can be through software applications as well. And then how do you classify the coupling that's taking place? Generally, it's based on where the decision-making is occurring, whether it's centralized, decentralized, or distributed. And then, the importance of the dependency analysis we talked about briefly based on how systems fail. And then criticality analysis, how do you define what's critical, right? Could be regulatory, safety, security, resiliency. You have to define your own parameters. And then for cyber hazard loss analysis, here's the detail behind that. In addition to MIT's system theoretic process analysis, MITRE has Terra. Threat assessment and remediation analysis is another method I would recommend. And then your cyber risk management strategy design, NIST SP 800-39, even though it was published in 2012, is still somewhat relevant. But basically, you have strategic and tactical cyber risk. So strategic, you have a control plane on your digital operating environment. That's your cybersecurity program. Then you have your operating plane where you have your tactical cyber risk, where you deploy your security controls or countermeasures to help maintain your continuity of operations in that plane. Okay, so that's really it. Any questions, real quick? Yes?
The slide deck be available somewhere.
If you email me at greerj.edu, I'll send it to you. All right, I'm not sure what the conference does, but I'm happy to share.
There's a lot here on unpack.
Okay, there you go. I'm happy to do that. And then if you have any questions, you can just follow up. All right, so just, if you need my email, see me outside and I'll get it to you. Okay, any other questions? Any constructive feedback? It's a very specialized area. Each ship has 3 different types of networks at least, right? So you've got the NMEA network on the bridge, serial bus network. You've got your Ethernet network for the commercial side of the ship, and then you have all the specialized industrial networks below decks, Modbus, Profibus, whatever they're using there. And increasingly, there's integration points between the networks. So how do you manage the integration from a security point of view? But I like this holistic approach. Because so many people work on just a component, right? But ultimately, you have to secure the entire environment. Yes?
So it's like the aerospace residents on the other side. So like when they usually build the ship, it's usually the manufacturers who lots early provide all the means training, all the training devices for it. In the ship industry, is it the manufacturer's responsibility to build those training devices, or is it kind of just open for government agencies?
It's not the same. So I didn't mention it, but to expand on this, I'm looking at simulators that parallel the work tools to make this all work. Okay, so I think I've run out of time. So thank you very much for attending today. It's something I'm very passionate about. So thank you.